Hello friends, I am Lalit Vasist and you are watching Engineering Made Easy. I hope you are enjoying my videos. So today's optical fiber topic is dispersion in optical fibers. So here we will discuss what is dispersion and how it affects the transmission in optical fiber communication. So let's first understand what we mean by the dispersion in optical fibers. Okay, so it is nothing but the broadening of the transmitted light pulses when it moves along the optical fiber. As the light rays move inside the optical fiber, then it starts to broaden. The pulse starts to broaden. I will show you how it takes place, what is intersymbol interference, and how it affects the communication process, what are the losses. So when the light ray propagates inside the optical fiber, as it moves further into the optical through the optical fiber, it starts to broaden, its width increases. So here it is this broadening of the light pulses is known as the intersymbol interference, ISI. We call intersymbol interference as ISI in short. So let's see what is this. Look at this here. Suppose I want to send a digital bit pattern of 1011. This is the digital bit pattern that I want to transmit through the optical fiber. So these are the pulses. In this digital bit pattern, the presence of pulse is 1 and absence of the pulse is 0. So 1011 is the digital bit pattern I want to transmit through the optical fiber. Now look at this. When this is the input end and here is the output end after traveling through the optical fiber. This is the optical fiber, and this digital bit pattern, when transmitted through this optical fiber, then due to dispersion phenomena, what happens, this pulse starts to broaden. The width of the pulses increases. You can see here also that these three pulses are shown here. This is the first pulse, this is the second and the third pulse. So you can see that there is overlapping between these pulses. This portion which I have marked in red color is the intersymbol interference, ISI. This is the ISI effect. So look that this is the common area, overlapped area between this pulse and this pulse. This is the region of this pulse and this pulse. So this is a common area, and between this pulse and this pulse is the common area. This is the common area of these two pulses. So this phenomena is known as the intersymbol interference. So look at this, that here I can easily identify the pulses, these digital bit patterns, that it is 1011. But what happens here this 1 and this is 0. So here this 0 is not present. No 0 level is present at this. This is indistinguishable. We cannot identify, we cannot separate this pulses at the receiving end or at after some distance when it has traveled through the optical fiber. So zero pattern, the 0 level is missing here. This creates problem when we want to separate the pulses at the receiving end. This is the intersymbol interference. So the dispersion causes this phenomena to occur, intersymbol interference. So now we will see different types of dispersion in optical fibers. Here we have two kinds of dispersion. First is the intramodal dispersion and another one is the intermodal dispersion. The another name for this intramodal dispersion is chromatic dispersion, and its another name for the intermodal dispersion is modal or mode dispersion. Keep this in mind. So we will first understand what is intramodal dispersion. Actually, this intermodal dispersion is present in all types of fibers, while this is present in multi-mode step index and graded index fibers, this intermodal. Okay, so what we mean by intramodal dispersion? Actually, you know that intra means within something and inter means between some things. So intra means within a mode itself, and intermodal means between different modes. Okay, so this is clear by the name itself. As we know that optical fibers may support either one mode or multiple modes. When the optical fiber supports only single mode, it is known as a single mode optical fiber, and multi-mode optical fibers support multiple modes. As I told you that this intramodal dispersion is present within a single mode. So This intramodal dispersion will be present in all types of fiber, whether it be single mode or multi-mode, because it has a mode. Where there is mode, intramodal dispersion will be present. But this intermodal dispersion is present in when we have different various modes. So it is not present in single mode, because only one mode is present in single mode fibers. So this is present only in multi-mode kind of optical fibers. Let's discuss it first. Intramodal dispersion. Actually, this intramodal dispersion results from the finite spectral bandwidth of the optical source. Okay, since optical sources do not emit just a single frequency but a band of frequencies, multiple frequencies are present in the light that is emitted by the optical source. So there is some propagation delay difference. Okay, propagation delay difference between the different spectral components of the transmitted signal. This causes the broadening of each transmitted mode, and we see the intramodal dispersion in the optical fiber. Here you also need to notice one thing, that this delay difference, okay, the delay difference may be because of the dispersive properties of the waveguide material, which is known as the material dispersion, or this delay difference may also be because of the guidance effects within the fiber structure, which is known as the waveguide dispersion. So there are two kinds of intramodal dispersion, because of the material dispersion and the waveguide dispersion. So this was about the intramodal dispersion. Now we will look at what happens in intermodal dispersion. What happens in intermodal dispersion, which is also known as modal or mode dispersion. So now I will show you a beautiful diagram. Let me draw it, where I will show you how the wave travels, light rays travel inside the graded index optical fiber. Okay, so this is the cladding, you know it already, and the central part in blue is the core of the graded index fiber. So how the light rays propagate inside it, let's see it. As we know, the propagation of the light rays takes place due to total internal reflection, and it is confined to the axis of the it is confined to the core only. You can draw any number of light rays through it. So one more light ray, let me draw it. It's not necessary that it touches the core cladding interface. It may be somewhat closer to the axis. This is the axis of the core, and it may also travel close to the axis, okay, in this direction. So let me show you how this propagation of light rays takes place. But before this, let's draw this graph. Here the distance, radial distance r, here the core axis. Let me draw a few dotted lines by extending it to make the graph clear. As we know that in the cladding area, since this is cladding and this part is cladding, we have a constant refractive index N2. So in this regions, both regions, we have N2, and in the core it varies parabolically. So it is parabolic change. This is the refractive index as a function of r, and here is the radius. What is a here? In this explanation that I have used here, the a that I have used was the radius of the core. Okay, keep it in mind. So here is the radius of the core. Now you can see it is N2 in the constant in the cladding area, and it is varying parabolically in the core region. Now I will tell you how the wave moves and how its propagation is different when we compare its propagation with the step index fibers propagation. although both use the total internal reflection, but the basic difference is present in the structure itself, that its core cladding and the refractive index at the core cladding interface does not change abruptly or suddenly. No step change is present. So the behavior of movement of the light rays that travels changes in both types of fibers. So how it takes place? See here. Here I am just drawing the core part, as I'm going to show you how the light rays are traveling inside the core. So I'm just showing you the core only. Okay, as I told you, this is the axis of the core. As I told you that the refractive index is maximum at the core axis, and as we move towards the core cladding interface, that is at these 2 points, it decreases. It is maximum at this core axis, and it decreases in this direction and in this direction also. So I am just drawing few dotted lines to show you that it is decreasing as we move from this center to the core cladding interface. The refractive index decreases. Clear? And also as we move in this direction too, the refractive index decreases. So now I will show you how the light rays are moving and why it is happening. If some light rays traveling in this way, then it will go like this. Why? Let me show you. Suppose here we have since I told you what is total internal reflection, the total internal reflection takes place when the light rays move from some denser medium to the rarer medium. Here it has suppose N1, N2, N3 and N4. Then N1 is more than N2, N2 is more than N3 and N3 is more than N4. So it is decreasing. So it is continuously moving from a denser medium to the rarer medium. So if this is the normal ray, then it will deviate away from the normal, and here it is the normal, and if it is the normal ray, normal line, then it will deviate away when it is moving from the denser to rarer medium. And in this case, when it returns back, okay, with total internal, due to total internal reflection. And you can see it also at these interfaces, as it is in this case, when it is returning back, it is moving from the dense rarer medium to the denser medium, so it will come close to the normal. Got it? So it bends and the total internal reflection takes place. This is nothing but the total internal reflection. In short, we name it as TIR, total internal reflection. So I think you got it. This is the maximum refractive index, and here we have minimum refractive index. So in this way the total internal reflection takes place, while in case of step index fibers it was constant. Throughout the core it was constant. So, and the change was at this when we encounter the core cladding interface. So it was not in this curve way. Here it is constantly refracting from moving from denser to rarer, and here from rarer to denser it is coming close to the normal. So total internal reflection is taking place. So as the light rays, one more thing, as the light rays travel slower in high refractive index mediums, you know it. So since here the maximum refractive index is at the axis of the core, so the light rays traveling along the core axis or near the core axis, okay, they travel slower in comparison to the rays which are moving away from the traveling away from the core axis. Okay, so but the light rays which are traveling away from the axis have to travel large distance. This creates a compensating phenomena to reduce the dispersion in the graded index fibers. Let me show you it. As you can see in this diagram, that here we have different light rays. So this light ray is traveling, this in brown is traveling closer to the axis of the core. So as it is a denser medium, and in denser medium light rays travel at slower speed, but the good thing is when various light rays are projected into the entering into the fiber core simultaneously, then since this is moving slower but it has to travel less distance, and here the rays away from the axis are traveling long distance, but due to since they are in maximum time, they are present in the rarer medium, okay, away from the axis, so they are traveling at faster speed. So it is compensating, it is creating compensating effect, because it is traveling slower but less distance, it is traveling faster but more distance it has to cover. So they reach to the end almost simultaneously, so it reduces the dispersion. So if we compare, dispersion is more in case of, if we compare graded index and step index, so the dispersion is more in case of step index fibers. Okay, so keep this in mind, since for near rays the core axis has to cover the shorter path lengths. Okay, so this causes a reduction in the dispersion. These rays reach to the other ends almost simultaneously due to this effect. So multimode graded index fibers offer low dispersion. Hence multimode graded index fibers are better in terms of low dispersion and high bandwidth in comparison to multimode step index fibers. Now we will see the order of intermodal dispersion. We now know what is intermodal dispersion. So here is a comparison of intermodal dispersion level in different kinds of optical fibers, like multimode step index, multimode graded index, and single mode step index fibers. So look at this comparison. As I told you about the dispersion, that here we have the pulse at the input side and this is the pulse at the output side, and you can see that this is of same width at the input side in all three kinds of optical fibers. But at the, if you see at the output end, if output end of different kinds of optical fibers, this pulse width is of different width. So look here, this is of maximum width. So multi-mode step index fibers offers more dispersion, it creates more dispersion, ISI effect is more in this case. And in case of multimode graded index fibers, the dispersion is lesser in comparison to multimode step index. And if we see further, then in single mode step index fiber, this dispersion is very less. Okay, so single mode, as I told you that this intermodal dispersion is generally not present in case of single mode fibers, because it only carries only one mode. So there is no chances of intermodal dispersion in case of single mode fibers. So you can see this comparison here, that as we move downwards from multi-mode step index fiber to single mode step index fiber, the dispersion level decreases. So this was all about the dispersion and its types and the comparison of dispersion in different kinds of optical fibers. I hope you liked the video. If you liked it, please don't forget to like and share the video, and please subscribe my channel Engineering Made Easy for more such informative and helpful videos. Thank you for watching. Bye.